Now, the chapter is laws of motion. In this chapter, we already know that according to the Newton's second law, the force acting on a body or external effort applied on the body is directly proportional to rate of change of momentum, where proportionality constant is k and the value of k is 1. Therefore, F is equal to dp by dt. Now, P is equal to m into v. F is equal to d by dt of m into v. F is equal to m d by dt plus v dm by dt according to product rule of differentiation. Case 1. If v is equal to constant, then F is given as v dm by dt. This equation use in case of variable mass. Case 2. If m is constant, then F is equal to m du by dt, where du by dt is equal to a, means force is equal to mass into acceleration. That one. Now, the application of Newton's second law. Net force acting along A on a body is equal to mass into acceleration. Net force where sigma F is equal to m into A. Now, case 1. If F is equal to 0, means no external force is applied, that is dp by dt is equal to 0, then P is equal to constant. P, which is a linear momentum, means mv is equal to constant. This is also called principle of conservation of momentum, means m1 v1 plus m2 v2 plus m3 v3 for n particle system is equal to constant. We also write m is inversely proportional to the velocity and the graph is given here. Again, if F is equal to 0, then m dv by dt plus v dm by dt is equal to 0. Now, m dv by dt is equal to minus v dm by dt. M dv is equal to minus v into dm. This equation is used generally for variable mass. It is used to determine the upward thrust acting in case of a rocket or of a variable mass system. We have F is equal to m dv by dt, F is equal to minus v dm by dt, where negative sign represent that the direction of upward thrust is always opposite to the direction of rate of change of mass. Application of Newton's second law means we have net force along A is equal to mass into acceleration. Let one example is there. If F force applied on a body along this way, then acceleration is acting along this way, and m into A is act opposite to the action of that one. M into A is called pseudo force. Now we discuss some problems on basis of pseudo forces. Problem based on pseudo force. First example. Find the horizontal acceleration given to the wedge to keep the body of mass m on a plane. Now let's draw the free body diagram. Weight of the body is acting vertically downward. Normal direction perpendicular to the plane. Mg sin theta along the direction of plane vertically downward. And whole system is accelerated along A, that is mass into acceleration acting opposed to that direction, which is pseudo force. The angle theta and this angle are equal, hence we say ma cos theta opposite to the direction of mg sin theta and ma sin theta is along the direction of mg cos theta. In this equation, the value of r is given by r is equal to mg cos theta plus ma into sin theta. Now we have to determine that find the value of A to keep the block of mass m rest on a wedge. Means the mg sin theta must be balanced by the force, component of force ma cos theta, which is acting opposite to it. To keep the body at rest, mg sin theta is equal to ma cos theta. Now m and m is cancelled out and A is equal to g tan theta. Example second. A block of mass m kept on a smooth inclined plane, if the whole system is accelerated horizontally so that the mass remains at rest, find the force applied by the mass on the wedge or inclined plane. This equation is also a part of the previous example that we have from above example. R is equal to mg cos theta plus ma sin theta. This is where R is a normal reaction, means it is a force applied by the mass on the wedge or force applied by the wedge on the mass. We have A is equal to g tan theta from the example 1. Then R is equal to mg cos theta plus mg tan theta into sin theta. We substitute the value of A in the equation. Now R is equal to mg. This equation can be written as cos square theta plus sin square theta upon cos theta. R is equal to mg by cos theta. R is equal to mg sec theta. This is the force applied by the block on the wedge or by the wedge on the block. Next example. A bob hang in a car and a car accelerates such that it is inclined theta with the vertical. Then find the value of acceleration of car. Now, if car is accelerated horizontally, then m into a acting opposite to that one. This is called pseudo force. If this is the string and it make an angle theta from the vertical, then weight vertically acting downward, ma opposite to the tension T in the string. If this angle is theta, then this angle is also theta because it is alternate angle. T resolve along theta, T cos theta, and perpendicular it's T sin theta. If the bob is at equilibrium, then we have T cos theta is equal to mg and T sin theta equal to m into a. Divide both equation, we have tan theta is equal to a upon g and a is equal to g tan theta. Now we consider some more example of friction or rough plane. We have a simple example that a block M and a wedge of mass capital M or huge mass body both are kept in contact. Find the value of A on the system so that the block M remains rest with respect to capital M. Again, the horizontal plane is smooth and the vertical wall of the plane is rough. Now, if acceleration is A, then the pseudo force acting M into A opposite to the acceleration. R, which is a normal action always acting perpendicular to the contact of a plane, weight of a block acting downward, and friction force opposite the motion means it acts vertically upward. Now we have R is equal to M into A, where friction force is equal to M into G. This is the condition to keep the body at rest. Friction force is equal to mu into R, where R is a normal action, means put the value of R in this equation. R is equal to M into A. Mu M into A is equal to M into G. M and M is cancelled out. A is equal to G upon E. This is the minimum acceleration applied on the system to keep the block at rest. Means acceleration must be greater than or equal to G upon U, mu, to keep this block of mass M rest on a huge mass of body capital M. Now one more example based on the friction force. Find the minimum force required to keep the block of mass M on the rough vertical wall. Now when a block of mass small m kept the wall, it always fall vertically downward because mg weight is acting downward. Now where R is 0, but you applied a force F opposite to R. Now R is equal to F, where R is a normal action, F is a force applied. If the body is at rest, or to keep the body at rest, the weight which is acting vertically downward is must be equal to the friction force which opposes the fall of a body. Means mg is equal to mu into R, where R is equal to F, means mg is equal to mu into F, and the force, necessary force required to keep the body at rest on the vertical wall is given by F is equal to mg upon mu.